We are looking at a table of standard reduction potentials. Standard meaning the temperature is 25 degrees Celsius and any aqueous solutions are 1 molar. And if we recall, reduction means the gain of electron. So if we look at silver, silver plus 1, if it was dissolved in solution and gained an electron, would be reduced to the element silver. So elements have a charge of 0. And if we remember from the activity series, that table is written in terms of oxidation. I'm going to pull that up here. So oxidation, if I look at silver, is at the bottom of the activity series, meaning silver does not like to be oxidized. So written as an oxidation, silver metal with no charge would lose an electron to become silver plus 1. And it's just by convention that the activity series is listed in terms of oxidation reactions. And the table that we're going to use, the values are written in terms of reductions. But if we consider lithium, which is on the activity series, lithium metal is the most easily oxidized. So these are the column 1 and column 2 metals. They're very reactive, so we rarely find them as the elements in nature because they're so eager to get rid of electrons. So if we recall, lithium is in column 1. So if lithium is around a nonmetal, it's going to lose exactly 1 electron, as is sodium, potassium, and rubidium. If magnesium, calcium, or strontium are in the presence of a nonmetal, then this column will lose 2 electrons, and its charge in a compound would be +2. So metals in the first or second column are very easily oxidized. If we go and remember the charges for ionic compounds, we put a -1, a fluorine atom, chlorine, bromine, or iodine. These atoms like to steal electrons from metals so that their noble gas configuration is met. So the nonmetals get reduced by oxidizing metals. And oxygen, the element is an oxidizer, so each atom likes to steal 2 electrons from a metal. So we know that fluorine likes to be reduced, and lithium likes to be oxidized. So what we're going to do is look and compare this to some values on the reduction potentials. So if we look at lithium, if lithium is reduced, this is not favorable because lithium prefers to be oxidized instead of reduced. So we're going to see a sign convention, and a negative reduction potential is going to be not favorable. If we find fluorine, on this table of reduction potentials, we see the element fluorine gas turns into 2 fluoride ions. So F-1, the reduction is very favorable. In fact, fluorine loves to steal 1 electron. And so this, a positive value, is going to be favorable. And we just finished looking at other thermodynamic values where the sign convention tells us whether or not a reaction is spontaneous. So we're also going to be considering the sign convention in this chapter also. Okay, so if we remember, I'm going to discuss potentials, what we mean by that. That's another word for voltage. And the unit for voltage is a V. So the potential, we might be asked for the voltage or the cell potential, or we might be asked for E0 cell. We also might be asked for the EMF, and the EMF is electromotive force. In this case, force is not strictly a Newton, the way a force is defined in physics, but there's a lot of terms that describe the same thing. So when we're using this table, we're going to note that for a chemical reaction, we're going to look at half reactions and either use Hess's law, and Hess's law, recall, means if we run a reaction backwards, or if we write it backwards, we would just simply change the sign of the value. And there's another thing I wanted to discuss here, and that is the half reactions are listed. There can't be oxidation without reduction, and vice versa. So these half-cell reactions are defined in terms of a standard hydrogen electrode, which I'm going to show us down here. This value for the potential is just defined as 0. So when these measurements were made, they were made in reference to the standard hydrogen electrode. So when we learn how to draw an electrochemical cell where we have two different metals, or possibly the same metal with two different concentrations, we'll be calculating the potential of that cell, or the voltage of the cell. And I'm just going to give us the formula when we do that. For example, E cell is, when we do this calculation, it's always going to end up being the big number minus the small number. And if we think about that, if we do this calculation, that means E, the standard cell, standard conditions with the little circle, E0 cell is always going to be a positive number. So if we have two metals that are connected by a wire, or two metals at two different concentrations where we have those half cells connected by a wire, then there is going to be electron transfer. And so the sign of E cell, when we calculate this will always be favorable. And we're going to end up talking about spontaneous and how this relates to Gibbs free energy. So E cell being positive means we're going to have a spontaneous reaction. And if we think about that, that should make sense, because if we put two metals together in a cell, then because of nature and the activity series, electrons will definitely flow in a direction according to this oxidation or activity series.